Hello students, this is a demonstration of checkpoint 3-3 projectile motion, which is based on sections 3.6 and 3.7 in NITE. If you want to follow along with the solution method, a great example to follow along on is example 3.12, and that's on page 84 in NITE in chapter 3. So I'm going to use the same solution procedure for this checkpoint problem. I have a projectile. It's launched at a 30-degree angle from the horizontal with a velocity of 15 meters per second, and we have 4 tasks. The first task is to draw and label a motion diagram of the trajectory that includes accurate spacing in the horizontal and vertical directions, the velocity vector at each point, the acceleration vector at each point, and the initial velocity vector. And once we have that, we need to go on to part B, determine the horizontal and vertical components of the initial velocity. C, determine the time in air for the projectile, and D, determine the range of the projectile. So let's get started with that. Now part A is something that I should do for any problem as soon as I start. And that is to draw some sort of diagram. I always want to have my diagram, my knowns, and my principles. So I know that I'm going to have some sort of vertical axis, some sort of horizontal axis. Let's call this A. I have an X direction and also a Y direction. Now I'm given in this problem that the projectile has some initial velocity that from which it leaves from the origin, and that's at an angle to the horizontal. And once it leaves the ground, once it's in flight, this projectile is in free fall. I know it's in free fall because the only significant force acting on it is the force of gravity. And this tells me that AY is going to be equal to negative G throughout the entire flight. And because I know that there are no other forces acting on the object, then it's also pretty straightforward to say that the acceleration in the X direction, in the horizontal direction, is going to be 0, because there are no other accelerations. This is sort of the definition of free fall. Now we also know that in two-dimensional motion, we can consider the horizontal motion separate from the vertical motion. So let me just consider the vertical motion first. If the object is in free fall, then I know, just like a ball tossed straight up in the air, if I start at 0 and then I'm here after some amount of time, and the ball or the projectile is slowing down, its acceleration is negative. Its acceleration is negative. So the spacing between the dots on my motion diagram is going to have to get closer and closer and closer every time. Whatever this distance is right here, it must be longer than this distance over here, because I'm moving a smaller distance in the same amount of time at each time frame, because I'm slowing down. However, in the horizontal direction, because there's no acceleration in the horizontal direction, my velocity is going to remain constant. So my motion diagram dots in the horizontal direction are going to have equal spacing all the way through. So if I were to, let me do this in red so it's easy to see. Here's my first dot, there's my second dot, third, fourth, fifth dot, let's say, and it's going to make its way all the way back down. And when it comes back down, it still has the same spacing, because I'm assuming that we're moving at a constant velocity in the horizontal direction, and it just comes straight back down. Oops, and let me actually correct that dot. Should be up here, and then it's going to come straight back down at the same height each time. Okay. Hitting the ground, back down over here. Notice that I haven't put any numbers on this diagram yet. All I've done is recognize that this object is in free fall, so in the vertical direction it's going to slow down, eventually turn back around and speed up, in the negative direction, and in the horizontal direction it's going to have equal spacing of the dots because the object is at constant velocity in the x direction. Now, a couple other things that we were asked to put on here. We've got our accurate spacing in the horizontal and vertical directions. I need to put a velocity vector at each point, the acceleration vector at each point. And I've already put the initial velocity vector on there, so let's just add my velocity vectors and my acceleration vectors. I'm going to do the velocity vectors in blue just to make it distinct from the dots, but each dot is moving towards the next dot. So if I were to measure my velocity at that instant in time, wherever that dot is, it's always pointing towards the next dot because that's where it's going to end up. The acceleration vector, so I will say v, 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 and v. Now the acceleration vector is also pretty straightforward because I know that at every point for an object in free fall, my acceleration is pointed straight downward. Magnitude is g. So here is an acceleration vector. Here is an acceleration vector. Acceleration vector. And same all the way down. Okay, because at every point the object is in free fall. There are my acceleration vectors and velocity vectors. And I've labeled my initial velocity, which is down here. That first velocity vector is my initial velocity. It's what I started with.
Okay, now let's consider part B of the checkpoint, which was to determine the horizontal and vertical components of the initial velocity. That can be done with vector algebra. If I know that I have some velocity vector, and here they told us that it's at 15.0 meters per second, I can always break any vector down into a component that is purely in the horizontal direction. In this case, I'm going to call that Vx. And there's also a component that is purely in the vertical direction, and that's going to be called Vy. If I set up a triangle, I know that this angle is 30.0 degrees, because I've launched my projectile at an incline. I can set up some trigonometric relations. We know from our basic trig relations in geometry class that if I take the adjacent angle over the hypotenuse, the value of that fraction is going to be equal to the cosine of that angle. So from this basic trig relation, we can set up that the horizontal component of my initial velocity, Vx, is going to be equal to 15 times cosine of 30 degrees. And if I do that out, I'm going to get 12.99, or we'll say 13.0 meters per second. This is the value of my initial velocity in the x direction, the horizontal component only. It's fairly straightforward to set up a similar triangle for the y direction, and through similar trigonometric relations we get 15 sine theta, and we know that theta is 30 degrees of that angle. Sine theta, or sine of 30 degrees is just 1/2, so what I have is 7.5 meters per second. So I'm done with part B. I've found the component of the initial velocity that is just in the horizontal direction, Vx, and I've also found the component of the initial velocity that is just in the vertical direction, Vy. Okay, let's go on to part C, which is determining the time in the air for the projectile. And in order to do that, I'm going to have to choose one of my directions, horizontal or vertical, and use it to find delta t, which is the time that the projectile spends in the air. In this case, I want to use the vertical motion only. And the reason I want to do that is that the limiting factor on how long this projectile is going to be in the air is basically how long it's going to return back to the ground. If I launch it up into the air at some angle, eventually it has to return back to the ground. If gravity was not acting on this projectile could just keep on going forever and ever and ever and ever. Nothing would be accelerating it back down to the ground. So the effect that brings it back down is the acceleration due to gravity. So that's going to determine how long we can actually stay in flight. And we're looking for delta t. And I just want to write out my displacement acceleration equations in the vertical direction. So I know that the change in my y position is equal to my initial velocity in the vertical direction times delta t plus 1/2 acceleration in the vertical direction times delta t squared. These values are known from my initial diagram. One thing which it may not be obvious that we do know is delta y. We actually do know delta y. If my projectile starts on the ground, which is at 0 height, it goes up to some height up over here up in the air, and then it descends back down and hits the ground, the change in its y position over the course of flight is 0. It actually returns back to the same y position that it originally started from. So delta y is actually 0. I'm going to say 0 equals Vy initial, which we found over here to be 7.5 meters per second, times delta t plus 1/2 negative 9.8 delta t squared. And now this is not immediately straightforward, because I look at this and I say, well, I have a delta t and I have a delta t squared. But if we think about it, this is just a polynomial from algebra. If I were going to factor a polynomial and solve for the unknown, what I would do is factor out that delta t. I'm going to factor out a delta t. So here's one term, delta t. And then that delta t gets distributed among 7.5 minus, let's get that negative sign out of there, minus 4.9 delta t. So now I have two terms. The only way that this equation could equal 0 is if either this term is 0 or this term is 0. Because you have to multiply something by 0 to end up with 0. So I have two options. One option is that delta t is 0. That could be one possible answer, and it works. The problem is it's not a very useful solution, because delta t equals 0, what that physically means is the very beginning at time 0. And it's kind of obvious to say that if no time has passed, the projectile hasn't moved at all. That is a true statement. It's just not very useful. So we call that the trivial solution. And by trivial, we mean it's technically true, but it's boring. It's not very useful. If no time has passed, the object hasn't gone anywhere. Big deal. So the only other way for this quadratic to be 0 is if this term over here, the 7.5 minus 4.9 delta t, is 0. So let's figure out what that gives us. If 0 equals 7.5 minus 4.9 delta t, the first thing I want to do is subtract 7.5 from both sides. So I have negative 7.5 equals negative 4.9 delta t. And if I divide both sides by negative 4.9, what I'll end up with is that delta t, the time in flight, is 1.53 seconds. And that is also a solution to our quadratic equation, but it's much more valuable than the trivial solution. My change in height is 0 at 0 seconds, but it's also 0 at 1.53 seconds, which means that's how long my projectile was in the air. And that's part C. once we know part C, once we know the time in the air, then the range of the projectile becomes fairly straightforward to find out as well, because now all I need to do is switch to working in the horizontal direction. If we're being asked how far is something going to travel, its range, then we're talking about its horizontal motion. So let's just write our displacement acceleration equation in the horizontal direction. I have delta x equals the initial x velocity times delta t plus 1/2 ax delta t squared. I'm lucky in this case. Ax is 0. Back up here when we drew our problem out, we decided that delta x is 0 because this is an object in free fall. Any object in free fall is moving only under the influence of gravity. So I actually get to cancel out this entire term because ax is 0 and anything times 0 is 0. So that goes away. Let's plug in what we know from what we have left. The initial velocity in the x direction I found in part B, 13.0 meters per second. And I just found delta t from part C, which is 1.53 seconds that this projectile is in the air. And if I multiply these two together, I get a value of 19.89. I'm only allowed to use 3 significant figures here, so I'll just round that up to 9. 19.9 meters. So about 20 meters downrange is the range of this projectile. So let's recap really quick. What did I do to solve this projectile motion problem? Step 1, I drew my problem. I recognized that this object is in free fall. It's in free fall because the only significant force acting on the object is the force of gravity, which gave me 2 important pieces of information. One, that ay is equal to negative g at all points in flight, and that ax is equal to 0 meters per second squared, because there's no change in my horizontal motion. I gave myself tick marks on the vertical axis so that I could draw an object that is accelerating vertically, that comes to a stop in the vertical direction and then accelerates back downward. And I gave myself equally spaced tick marks in the horizontal direction because in projectile motion, as long as we're not considering air resistance, the horizontal velocity is going to remain constant. Then I solved for the components of my initial velocity. I did that by setting up a triangle. I knew the angle of release from the horizontal at 30 degrees. I used my trig relations to set up the fact that the horizontal component of velocity was v cosine theta. The vertical component was v sine theta. Then we went on to part C. I knew that the constraint on my time in air was going to be the force of gravity. It was going to be my vertical motion. I can only stay in the air as long as I'm not, I haven't hit the ground yet. So I use my vertical motion, my vertical displacement equation, to solve for delta t. I had to factor a polynomial because I wasn't lucky in this case. My initial velocity over here was not 0, so I had to keep this term. But I did so by factoring out a delta t and solving just like we would a quadratic equation in algebra. I found 2 solutions to that equation. One was delta t equals 0 seconds. Technically true, but also trivial. It's not a very useful answer. So I went with the other possible solution to the quadratic, which is that delta t equals 1.53 seconds. That must be my time in flight. Finally, part D, I switched over to considering the horizontal motion. I know that my delta t from part C is the same because once I hit the ground, my projectile has stopped moving. Plugged in knowns, my initial x velocity, the same delta t, and I get a change in position, or my range, of 19.9 meters. And there's an example projectile motion problem that you can use to use as an example on other similar problems.